Okay, Lily, I have investigated and I want to talk to you about concentrations, but before I do, I want to make sure I have the experimental setup properly assessed because I might have some suggestions on changes that we can do to make our lives easier. So, the current experimental setup that I think is happening should be that you have one experiment going on where you are treating collagen with MMP and varying the amounts of zinc inside of it, meaning that the zinc changes the amount of collagen breakdown because the zinc is affecting the MMP. The experimental setup number two that you have is that you have that collagen treated with MMP and you have some amount of zinc. We don't really know how much just yet, but we might be able to say a finite amount of zinc for all the trials, and that there are varying amounts of doxycycline for the variables. So this is the thing that would be the independent variable in this experimental arm. The reason we have to have some zinc is because zinc is the cofactor for MMP. So that means that it requires zinc to activate the MMP. Without any zinc at all, you won't have an MMP that is working at all. So therefore, we could have a couple of different controls. Control A would be a collagen with no MMP, which would be something that we can measure 100% strength at and absorbance. Um, Additionally, we could have a control that has inactivated MMP, as in we treat it like normal with a set amount of zinc, but we inactivate it first by chelating and stripping off that zinc, or with a heat inactivation. You know that heat is something that can uh, destabilize, denature proteins. Well, MMPs are proteins, they're enzymes. So if we use heat and burn the MMPs, we can denature it to the point where it doesn't work. And that could be a control that we prove. Um, this would show us that the MMP should work as planned because we can turn it off if it is unplanned, kind of thing. It's kind of like proving a negative kind of thing. And finally, that there would be a baseline sample with that set amount of zinc being the target for all of this change right here, that we can set the amount of zinc to be the same for the baseline and the experimental arm 2, and that we would change the amount of zinc in experimental arm 1 to see the different levels of MMP activity. So hopefully I'm getting this right, summarizing it the way you intended. Let us clear the ink and we will move forward. Because under those circumstances, I can tell you that the collagen substrate concentration, the collagen that we're working with, should be somewhere around 1 to 2 milligrams per milliliter. And this is standard across a couple of different papers that I read, specifically from a systematic review that is based on collagen from dental implants and stuff. That should be well sturdy enough to be able um, to work with it and cut it apart with the force gauge that we have, as well as it should be low enough that we should be able to see the degradation of the collagen at some measurable level. In fact, we could actually see if the 100% is 1 milligram per milliliter when we put in the spectrophotometer and we calibrate everything to be that 100% or lower, then let's say the absorption level of 1 year trials was 75%. Well, that means that um, your substrate, your collagen, has reduced by concentration from the MMPs down to 0.75 milligrams per milliliter. So that's kind of nice that you can do that with that standard 1 to 2 milligram to milliliter lot. If you wanted to use 2, totally fine, you would just double it. So if it was 75%, it'd be 1.5 milligrams per milliliter kind of thing. And that's just how we can infer how much concentration of the collagen is left in the sample after the MMP has done its job. The MMP concentration was definitely more tricky to look at because there's three different ones that work specifically on collagen substrates. There's MMP 13. That one is the most active of the three that I found that we could buy. And therefore, the concentration of that should be lower because it doesn't need as much to do its job. And the highest concentration that should be is 50 nanomolar. To remind you, molar just means moles of that object per liter. So the molar mass of MMP13 is somewhere in the hundreds and hundreds of grams per liter, which means it doesn't take very much to get a nanogram or a nanomole, excuse me, and therefore 50 nanomolar is actually 3 micrograms measured out into a milliliter. So not very much at all. This might be a problem later. We'll see in a moment here. First off, you can see that's a very small amount. How in the world do you even measure a microgram? The things that you have at the store are for measuring grams, not micrograms, one millionth of that. So how in the world do we do that? We will see in a second. But hear me out while we're looking at this. MMP8, which is the second most potent of them, the second most active in our bodies, that would be 250 nanomolar. It is 1/5 the strength of MMP13. So therefore, we would need 13.3 micrograms per milliliter. It has slightly a different molar mass than MMP13, but that is the calculation that I have for you. And then MMP1 is the least active of the three, and it's a little bit bigger of a molecule. So the highest we should get for a concentration should be 500 nanomolar. Notice that's 10 times as concentrated as the MMP13, which means you need about 10 times as much. In fact, if you look at the measurements, we would need 27 micrograms per milliliter for measuring, and that's more. We can definitely try to measure that, but we would have to do some dilution. Before we move on to the problems I see with those numbers, doxycycline concentration should be around 200 micromolar, which is bigger than nanomolar. That means that we can get 102 micrograms per milliliter. We can definitely measure something like that, or even better, the way that works out pretty easily is that most people, when I read stuff on doxycycline, make what is called a 10 millimolar stock solution because it's stable, and then we can dilute that down based on the 10 micromolar turning into 200, excuse me, the 10 millimolar turning into 200 micromolar. A micro is 1/1000th of a milli, which means that we would have to dilute it from 1 down to 50s parts to get the 200 micromolar. The math there is pretty easy. Zinc will be a zinc chloride solution, and we really don't need very much because we only need one zinc atom to associate with each of the MMP protease complexes, which means that 50 micromolar is going to be plenty for all applications. And if we did go ahead and do the changing amount of zinc for all of that, then we just do 50, 45, 40, 35, so on and so forth. Because if we do any more than 50, we can actually denature the collagen and the MMP by having too many of these metals that are reactive inside it. Because, of course, not only does the zinc react to everything, but once that zinc is stripped off to be used by the MMP, that chloride, those chlorine ions are very, very reactive, and that could cloud the uh, um, collagen and therefore make the collagen look like it's more concentrated than it actually is. So that's 6.814 micrograms per milliliter. You would have to make a solution that is 6.814 milligrams per milliliter and then dilute that by 1/1000th to get it to the right number. We will definitely have to do some other buffers like calcium chloride as well to make sure that the interaction between the zinc and the MMPs stay reactive, that the zinc, once it's been discarded by the MMP, doesn't go off and just reattach to chloride immediately, that the calcium takes up the chloride spot so the zinc can go back and do its job again and again. But we'll worry about that later because we have something new to worry about if this is the setup that we have. I did some math, and the MMP1, the least potent of all the MMPs, costs $520.50 for 10 micrograms. The MMP8 costs 506.50 for 10 milligrams or micrograms. And MMP13, the most potent, which is probably the one we would go with, is actually the most expensive at 562 or $562.50 for 10 micrograms. The reason it is so expensive is because it has to go through the same process that we did last year when we made our GFP molecules. As in, we have to have E. coli recombined with a plasmid in order to tell it to make MMP13. Then we have to harvest the MMP13 and put it all together. So instead of us doing that, we have to tell a lab to do that. And the lab gave us this quote here, which means that those prices and those amounts, 10 micrograms, is not a lot of this enzyme to get, which means that if we were to purchase the MMP13, you would only be able to make 3.3 milliliters, little tiny bit, little tiny vials of MMP13 at the concentration you would need to run even the most concentrated of levels. Yes, that does mean that if we were just to dilute it by half, then we would have 6.6 milliliters, and you would have more opportunities to do more testing and stuff. But that doesn't give you a whole lot of room to play with the MMPs and have something go wrong and figure out something else to do in the meantime. I don't even know how much MMPs are required to uh, to do the collagen degradation at the level where we can see it in the lab. So I don't know if the 3.3 milliliters of the what is the concentration, the 50 nanomolar. I don't know whether or not that's enough to see marketable results and have the maximums or the other numbers come down from that still be beneficial. So MMPs might not be the best way to go about this, but I'm smart, which means I found a solution. And instead of using MMPs that are derived from mammalian cells, MMPs that were made by E. coli from this uh, this recombination event that we have to have, maybe we can find a collagenase that is from another source. And wouldn't you know it, there is a Clostridium bacteria called Clostridium histolyticum. It's kind of this, just for side reference, it's the same bacteria family as the bacteria that causes botulism, because that's the same bacteria that actually allows us um, to get Botox. Like that's the toxin that they get for Botox to slow the degradation of calciums and or not calciums, collagens and cartilages, and have wrinkles not show up as quickly and and start the paralysis of nerves in your face so you don't have smile lines and stuff. So this Clostridium bacteria is kind of fun that we found a version of this that will supply a collagenase, what we call clostridial collagenase. It's still an MMP. It still requires a metal and still works on the matrix of collagen to break it down. We just call it collagenase because it is literally an enzyme that works on collagen. The nice thing about this is per reaction, it is about 10 to 100 times cheaper than the recombinant mammalian MMPs that we were just talking about. Now, if we were to go with this Clostridial collagenase, and there's many types that we could use, but if we were to go with this, there would be some changes that we would have to make to the experiment. One change is like we couldn't probably change the amount of zinc in the experiment as one of the variables. We'd have to get rid of an experimental arm in this case. The reason for that is Clostridial collagenase already has zinc tightly bound in its structure. It's already bound all the time. That cofactor has found a way to stay there at all times. So if we were to spike it with more zinc, it doesn't really change anything. We wouldn't have any more results. So that would be like me saying, hey, this is a model of someone who's getting more zinc in their diet. Well, it won't show us anything. And if we were to say, hey, this is a model of someone who doesn't get enough zinc in their diet, well, we would actually have to use a chemical chelator, which is a chemical agent that strips away the zinc from the enzyme in order to get that enzyme to not have the zinc already attached. So we would literally have to break the bonds inside the enzyme to get it to remove the zinc. And at that point, is the enzyme even going to function the way it's supposed to? Even if we do supply it with other zinc molecules, I don't know if it will. So we might have to remove the experimental arm on zinc alone, but that still leaves you the experimental arm on doxycycline. And as you see in the third point there, doxycycline can still inhibit. It's just a little bit of a different mechanism that you might have to do a little bit more background research on to see exactly how doxycycline interrupts Clostridial collagenases. I'm sure there's a paper out there about that. I just don't know exactly what the mechanism is off the top of my head. Um, the nice thing about this is that we don't have to think about collagenase in terms of concentration, because when bacterial samples are gotten for manufacturers and we take the enzymes out of them instead, like if I go and get insulin from a recombinant DNA technology from a E. coli cell that needs to produce it, yada yada, I need to know specifically what that source strength is in order to trust the insulin that I get, that it will work the way I want it to. But with this one, because it's not a human-based consumption, because we're not going to take in this collagenase in order to have it do things in our body, because we're only using it as a model, the manufacturers actually supply that information pretty readily. And therefore, we can think of it as different enzymatic activity levels, like the manufacturer will tell us, instead of worrying about, hey, I need this much collagenase per milliliter and drop it down like that. We can think of it like, oh, this enzyme will do this much activity, and if I do dilute it by half, then it'll do half as much activity. If I dilute it by half again, it'll do 1/4 the amount, and so on. So it actually makes your job a little bit easier if we decide to go this route. Okay. So I wanted to give you an example of what the math is here, because I know it's kind of throwing you a curveball. I can get collagenase 1 from this source, from Fisher Scientific, for $90 for 100 milligrams. That's already 1/5 the cost for 10 times as much. So that's 50 times better. We can do 50 as many activities. So that's great. Their strength for that $90 collagenase 1 is 125 units, meaning reactions, meaning how many times that itty bitty collagenase enzyme does its job. And we'll just call that units per milligram of the collagenase, which is 12,500 units at your disposal, which is great. That's a lot of testing that you can do. So let's assume that we wanted a solution, a stock, that would be working at 10 units per milliliter, meaning that it has only enough collagen inside that milliliter, excuse me, collagenase inside that milliliter to break apart 10 collagen units. Well, that math is actually kind of easy because we can backwards uh, backwards algebra our 10 units per milliliter. If I have a solution that starts off at 125 units per microgram. Okay, so those aren't the same number values there, but at least I'm closer to the result. I need to multiply some micrograms that I measure for my solution and put it in 1 milliliter of solution. So now all I need to do is find X because I got my units and my milliliters. So what is 10 divided by 125? Well, X would just be 0.08 milligrams. And I'm getting you 100 of those milligrams. So you could have virtually 100 of these stock solutions, and even if they degrade, even if they don't work, even like if you had to do one of these stock solutions a day, you would only use 1/10 of the total substances that we needed. And we can bump this number up to make it a higher concentration if you wanted to, a higher strength, as we should say now, a higher enzymatic activity level, we could say. Um, you can bump it down for the different amounts there. I don't think you should need more than 10 units per milliliter because you can still see the result of what's happening, and we could jump it down to 9, 8, 7, 6, 5, 4, 3, 2, 1. Or even more awesome is if we wanted to have that 1 milliliter of reaction solution, all we need to do from that point is use this equation to find out how many microliters or milliliters of that reaction solution, the stock solution, that I would need to mix with water. So say I have, say I want to make one for 1 microliter, excuse me, 1 unit per milliliter. Let me do the easy one I have up top first. Let's say I wanted one working solution, one test that was 0.01 units per milliliter. Not very much collagenates for your collagen experiment. Well, if I use C1V1 equals C2V2, and the original solution is 10 units per milliliter, and the one I'm looking for is 0.01 units per milliliter, and I wanted 1 milliliter of this solution. 1 times 0.001, or excuse me, 0.01 is 1, divided by 10 is move the 0 over, X equals 0.001 milliliters, which is just 1 microliter. And we can pipette that out very easily from your stock solution. So this setup does make your math a whole lot easier. This same equation, by the way, you might have noticed it as M1V1 equals M2V2. That's the way I learned it back in the day. Think it over. Definitely have a curveball here for you. If you do want to go the route of the crazy specific, crazy expensive NMP 13, then that would mean you only have 3 tries at this. You only have 3 things that you can test. And even if you did decrease the concentration of this MM13, that's $562 that I can't spend on other parts of your experiment. With a $90 price tag, I can spend a whole lot more on you and therefore buy your doxycycline, buy other things that could inhibit this, stuff like that. Think it over. Let me know. Hope this helped a little bit. Hope this math didn't make you go crazy. Good luck.